Hello, everyone. Welcome. Happy Wednesday to you. I hope you're doing well. I was playing with Letty Van Halen there because he died yesterday. I don't know if you heard that. Sad day. Rest in peace. Just one quick announcement here. We have an exam coming up next week. So make sure you have that on your radar. It'll be very, very similar in format to the previous exam. And so you can be ready for that. Sorry. We just have to finish covering a little material today, a little bit more on Monday. We'll do a quick review on Monday, and then we'll have the exam. Okay. Do you have any questions for me before I get started? Before we get going here. Okay, if you remember at the end of last time, we were looking at oxidation and reduction, right? So we're focusing on reactions that occur in solution. And at the very end, we started looking at oxidation and reduction, and we learned how to assign oxidation states to different elements within a compound, right? And the reason we want to be able to do that is so we can identify oxidation and reduction reactions, okay? So recall that oxidation is the loss of electrons, all right? We can see that when we assign oxidation states in a chemical reaction as an increase in oxidation number. In other words, when an element goes from a lower oxidation number to a higher oxidation number in a chemical equation, then we know it got oxidized. And if it goes from a higher one to a lower one, then we know it got reduced, okay? Reduction is the gain of electrons or a decrease in oxidation number. In a chemical reaction that involves oxidation and reduction, one thing is always oxidized and another thing is always reduced. They must happen together, right? Why? Because if something loses electrons, something else has to gain them, right? So oxidation and reduction occur together, all right? And so one thing is oxidized, the other one's reduced. The thing, the substance that is reduced is called the oxidizing agent. Why is it called the oxidizing agent? Because it causes the oxidation of something else, but it itself is reduced, okay? The reducing agent is a substance that causes the reduction of something else, but is itself oxidized, all right? So what we're going to do here in this example is identify the oxidizing and reducing agents in these reactions, okay? So let's start by, I'm just going to write down the reaction, the first one here, 3H2S plus 2NO3 minus plus 2H plus goes to 3S plus 2NO plus 4H2O, all right? So there's the reaction. The next thing I'm going to do is I'm going to assign oxidation states to every element in both the reactants and the products, and I'm going to assign that using the sort of rules that we looked at last time, okay? I'm not going to go over those again because we don't have the time. So if you don't have those down yet, don't worry. You can go back and look at that, okay? But when I'm assigning oxidation states along here, I start with this one. And I know that hydrogen is +1 from the rules, and sulfur is -2, okay? I go to the next one. The first one I assign here is oxygen, which is -2. And there's 3 of them for -6, and the total charge is -1. So nitrogen must be +5. Right? In order for the sum of these to be -1, because remember, the sum of all the oxidation states for an ion have to add up to the charge of that ion, okay? Here we have a monoatomic ion, right? So its oxidation state is just its charge, +1, all right? On this side, we have sulfur, pure element. What's the oxidation state of a pure element?
0.
0, correct. So that's 0, all right? Here we have NO. We go to oxygen first, -2. So nitrogen must be +2, right, to sum up to 0. And then we go over here to water. Hydrogen is +1, and oxygen is -2, okay? So I've assigned oxidation states to all of that. If this seems like a little bit of a mystery to you, this is what we did at the very end of class last time. And so you can go back and review that in the book if you need to, all right? So now we can look at these oxidation states and first of all determine, do we have a redox reaction? Do we have an oxidation reduction reaction? And the way to answer that question is, do any oxidation states change for any elements? And what do you think? Are there any changes in the oxidation states of any elements in this reaction?
For nitrogen.
Perfect. Nitrogen here, right, is going from what? +5 on this side to +2 on that side, right? So is nitrogen being oxidized or reduced? Is nitrogen being oxidized or reduced?
Oxidized.
Reduced.
Reduced, right? Reduced, because remember, reduction is a decrease in oxidation state. So here's the reduction, right? And then what substance here is being oxidized?
S.
Sulfur, yes, sulfur is being oxidized. Notice sulfur is going from -2 to 0, right? So it's going up in oxidation state. And so that's being oxidized, right?
I have a question.
Sure.
So it doesn't matter like how many molecules or atoms you have, it's always going to be like the same, like the charge that's not affected by how many atoms you have of them.
So when you're figuring out the oxidation state, you're just looking at the formula of the compound itself, right? So you can disregard this too, but you do have to take into account that 3, right? So for example, when assigning oxidation states to NO3-, the oxygen is -2, right? Again, you need to go back and review those oxidation state rules if this sounds a little foreign to you. It's -2. There's 3 of them for -6, right? And the total charge is -1, right? So whatever the oxidation state of nitrogen is, let's call it X for a minute, X plus 3 times -2 is equal to -1, right? So what must X be in order for this to be true?
I was actually thinking more about the hydrogen and sulfur together.
Here, right. So it's just individually, right? It's just for every individual atom. So you can, when assigning oxidation states, you can ignore the coefficient.
Well, like the H2S, because the H2 has a +1, but it's with the S that's a -2.
Right. So each hydrogen is +1. There's 2 hydrogens. You have to take into account that subscript. So that's 2+, and then the sulfur is 2-. So 2+ + 2- is 0.
Okay.
Does that make sense?
Mm-hmm.
So you assign oxidation states based on the formula of the compound. You don't have to worry about the coefficient.
Oh, okay.
Okay, good. All right, so if this is the reduction and this is the oxidation, then what is the oxidizing agent? What is the oxidizing agent?
Would it be nitrogen?
Right, so it would be, you can either say nitrogen or you can say the whole thing, NO3-. Typically you give the entire thing that's involved in the reaction. So normally we would say NO3-. And why is it the oxidizing agent? Because it is the thing that's being reduced. Are you with me? Okay, then what is the reducing agent?
So then the whole compound, so hydrogen sulfide?
Correct. Correct. H2S is the reducing agent because sulfur is being oxidized. Okay, let's do one more example. The
I have
second
a quick
one.
question.
Yes.
When we're finding the agents, do they always come from, because we're looking at the reactants, not the product?
Correct.
So
Yep.
they're gonna come from the reactants?
Correct.
Okay.
Correct. Yeah, good question. Okay, let's do one more example. So here we have MnO2 plus 4 HBr goes to MnBr2 plus Br2 plus 2 H2O. All right, and if we again assign oxidation states, in this case, we go to oxygen first, that's -2. There's 2 of them, so manganese has to be +4. Then over here, we go to hydrogen first. Hydrogen is +1, and then Br is -1. Here we go to bromine first. -1 times 2 is -2, and then that's +2. Br2 is a pure element, so that's 0. In H2O, hydrogen comes first, it's +1, and then so oxygen is -2. Abe, did you have a question?
Yeah, so when it comes to these like oxidation and oxidation reduction equations, we won't need to balance them. We'll just need to identify the oxidation states and the agents.
You might have, I mean, you'll have to balance equations for sure, and it might be a redox reaction, but we already learned how to do that. But you won't have to, I understand your question now. You won't have to balance any redox reactions in terms of splitting it up into half reactions and that whole thing. We'll go over that next semester.
Oh, okay. Yeah, that was my question. Thank you.
I get it now. Okay, sorry. Emily.
So when we're going through and doing this part, what's determining which why we would do oxygen first?
So this is what I covered at the end of last time.
I just can't.
So we're going to go through those rules that I gave you last time, and then you go down this hierarchical list when you get to the non-metals, right? So notice hydrogen goes before oxygen. This is the order in which you follow, right?
Okay.
And then plus the rules that I wrote down last time.
Perfect.
So again, if that, go back and review that, and you may want to have a quick look at it in your book as well if you'd like. Okay, Nayeli.
Hi. So is there a reason why you don't take into account like the number before the element, like the 4, when you're doing the oxidation states?
Correct, because the oxidation states is just within the compound. You don't have to worry about the coefficient.
Okay.
All right, awesome. So now we want to look and we want to say, okay, what is being oxidized here? What's being oxidized here? Remember, oxidation is an increase in oxidation state.
Is bromine being?
Bromine, correct. Bromine's being oxidized. Right, so there's your oxidation. And what is being reduced?
Manganese?
Manganese, correct.
Manganese.
Manganese is being reduced. Okay, so there's your reduction, right? It's going down in oxidation state. So what is my oxidizing agent?
Manganese? then?
Manganese.
Correct. MnO2 is my oxidizing agent. And what is my reducing agent?
Bromine.
Bromine. Bromine is being oxidized, so it's my reducing agent. And it's in HBr, so we're going to write down the formula for the whole HBr. Okay. So this is the oxidizing agent, and that's a reducing agent. This is the oxidizing agent. Why? Because it's being reduced and causing the oxidation of this. Yeah? Okay, very good. Gabby, did you have a question?
Yes, I am not following, but why Br is 0?
Okay. On those rules that I gave you last time, at the end of last time, sorry. Look back at your notes. Any pure element is always 0. Okay? Any pure element is always 0.
Okay, thank you.
Yeah, you're welcome.
I also have a question.
Yes.
So since there's 2 BR2s on the other side, do we just only take one of them into account, or?
Oh, that is, what do you mean? Oh, yes, right. So notice when it goes from here to here, that's not being oxidized or reduced. right? So that's not undergoing any oxidation and reduction. The only thing that's going to oxidation reduction is when you go from here to here. So out of these 4 bromines, only 2 of them are actually oxidized and the other 2 are not. Great question. Anything else? Alexander, do you have a question?
Yeah, can you go back to the first one that you did, just the what you wrote down? So for the, okay, so I see. So when you wrote down reducing agent, you chose the one that had the element that is that is oxidized, right?
Correct. Yep.
Okay.
Yep.
Cool. Thank
Okay.
you.
Very good. All right. All right. That's the end of our material for the solutions chapter. So we're done with that. And now we're going to start chapter 6, which is on gases. And luckily you already saw a pretty long video on chapter 6, so I'm not going to cover that stuff again. If you have not watched that video yet, make sure you watch it right after class, because I'm just going to assume you have for our purposes right here. Let's see, let me just get this going. Okay. Okay, so now chapter 6, we're going to move from solutions, right, to gases. All right, we're going to move from solutions to gases. And some of the things we did in solutions, we're going to see in gases. For example, we're going to see stoichiometry again in gases, right? This is our 3rd visit now to stoichiometry, right? We learned about stoichiometry first when we started looking at chemical reactions. Then we saw stoichiometry again in solutions, and now we're going to see stoichiometry again in gases, all right? Also, in gases, we want to understand their properties a little bit, right? So you saw that in the video, you learned about the different variables that define a gas, right? V for volume, N for number of moles, right? T for temperature, and always for gas law problems, you want to work those with the temperature in Kelvin, okay? Always in Kelvin. And then, what am I missing? P for pressure, right? P for pressure. So volume, you have a good sense of what that is. Number of moles, we already know. Temperature, we know. We haven't talked too much about pressure yet. Pressure is the force that is exerted by a gas on the surfaces around it. So if we think about a gas as a collection of particles like this in random motion, those particles are hitting surfaces. And because of that, excuse me for 1 second, let me just do that. They're hitting the surfaces around them. And the sum of all those collections is called pressure, all right? And so the air around us is exerting pressure on everything all the time, all right? And we report pressure in different kinds of units. Here are the different pressure units. We're going to primarily be using the torr and the atmosphere, all right? And millimeter of mercury, which is exactly the same as a torr, okay? You may have seen maps like this of weather. They put high pressure and low pressure. High pressure means there's more gas particles there at a higher pressure, right? And so that tends to be a sign of good weather coming in because it pushes storms away. Low pressure in a weather map draws storms in, and it tends to be a sign of bad weather coming, okay? You might also have felt a pressure difference in your eardrums when you change altitude, right? When you climb a mountain or when you go up on an airplane. And that's because your ears have pockets of air, and usually the pressure inside your eardrum and outside your eardrum is exactly the same. And so the eardrum is not stressed one way or the other. But when the pressure changes, for example, when you go up on a plane, the pressure outside of your eardrum goes down, and that causes the pressure inside of your eardrum to cause your eardrum to bulge outward, and that's what causes that pain, all right? So sometimes when you yawn, it opens up cavities that allows that to equalize, and then the pain will usually go away, okay? Pressure, the unit of pressure, millimeters of mercury, comes from the way that pressure is measured using a barometer. So a barometer is a pool of mercury in an evacuated tube. And what happens is that the atmospheric pressure pushes the mercury down and up this tube until the weight of the mercury matches the atmospheric pressure. All right, and that height is 760 millimeters of mercury, or 29.92 inches. All right, so that's where we get that unit. So I just want you to be familiar with these units and be able to convert between them, right? Because you're going to have to throughout the course of this chapter. Okay. As you saw in the video, different of these properties are related by what are called the simple gas laws. So you learned about Boyle's law, that volume is inversely proportional to pressure, or that V1P1 is equal to V2P2. You learned that volume is proportional to temperature, right? Or V1T over T1 is equal to V2 over T2. And that volume is proportional to the number of moles, right? V1 over N1 is equal to V2 over N2, right? So those are simple gas laws. I'm not going to do any examples on those because they're fairly simple and you already saw the video. I'm going to jump right into the ideal gas law. The ideal gas law is PV equals nRT, okay? It gives you the relationships between all these different properties of a gas that we just talked about, right? And here it's important to make sure you have the right units on everything, okay? So P is pressure in atmospheres, V is volume in liters, N is moles in moles, all right? R is called the ideal gas constant and has a value of 0.8206 liter atmosphere mole Kelvin, all right? And which is one reason that you have to have all these things in the right units. And then lastly, T is the temperature in Kelvin, right? So all gas calculations are going to be done in Kelvin, all right? The ideal gas law has in it all the simple gas laws, right? It's contained all in this, right? So it's a summary of all of them. All right, let's just do an example using the ideal gas law. So here's our problem. We're given that we have a volume of 10.0 liters, a pressure of 44.1 psi, a temperature of 27 degrees Celsius, right? And we're asked to find what?
How many moles?
How many moles of gas?
How many moles, right? We're asked to find N, all right? So this is fairly straightforward. All we got to do is say, oh, okay, wait a minute. Here's what I'm given. Here's what I'm trying to find. What equation relates these two things? And the first thing that should pop into your mind is the ideal gas law. PV is equal to nRT, right? And so you can see that you can solve that for N. N is going to be equal to PV over RT. So solving this problem is just a matter of plugging the right quantities into this equation with the right units, all right? So it's important to have the right units. And notice here, we don't have the right units. The units of volume are correct, right? But this needs to be in units of atmospheres, and this needs to be in units of Kelvin, right?
Kelvin.
So let's do those conversions really quick. We'll start with P. P is equal to 44 pounds per square inch, right? This is the unit we more normally use, like when we fill up our tires and our bikes and or our cars, right? And the conversion factor there is that 1 atmosphere is equal to 14.7 psi. So that cancels, and I get 3.00 atmospheres for my pressure, okay? Then for my temperature, it's given in degrees Celsius. I got to convert that to Kelvin. So I have to add 273 Kelvin. So that's equal to 300 Kelvin. And that is my least significant digit. Okay. So now we just plug in, right? N is equal to PV over RT. So the pressure, right, is 3.00 atmospheres, right? I'm plugging into this equation now. The volume is what?
10.0 liters.
10.0 liters, exactly right. The gas constant, 0.08206 liter atmosphere mole Kelvin, right? PV, so that's R. And then lastly, the temperature is 300 Kelvin. Now, there's a lot of different units here, and I want you to always cancel your units, right? Because it will show you your mistakes, right? So be very, very careful with units. Notice what happens here. Atmosphere and atmosphere cancel, right? Liters and liters cancel, yeah? Kelvin and Kelvin cancel. And what am I left with? 1 over 1 over moles, right? So 1 over 1 over moles is just what?
Just mole.
Just moles, right? So my answer comes out in moles. Is that what I expect? Yes, because that's what I was looking for, right? You with me? Any questions? Okay, I'm gonna have you try one. Go ahead and try this one. Okay, see if we can finish up the next few seconds. Okay, the right answer was D. And yay, you almost all got that. So outstanding. Thank you very much. Really quickly, right? You're given the volume, the pressure, and the temperature. You need to convert the temperature to Kelvin. Always work in Kelvin with gas law equations. And then you find N, and you just plug in N is equal to PV over RT. You plug all those things in, and you get 0.26 moles. Okay. Since most of you got it, I'm not gonna work out the rest of the details. All right, let's keep moving along. Molar volume. So the next thing we want to understand is the molar volume of a gas. In other words, how much volume does a mole of gas occupy, right? And as you might imagine, it depends on the pressure, volume, and temperature, right? Depending on what the pressure, volume, and temperature is, you're going to have different volumes of gas, right? So we're going to define something called standard temperature and pressure. So let's define first, let's just define molar volume. Molar volume, volume of 1 mole of a gas, right? And then I want to define something called standard temperature and pressure. Sometimes we call that STP, standard temperature and pressure. Standard temperature is just defined as 273 Kelvin. And standard pressure is defined as 1 atmosphere. All right. So when we talk about standard temperature and pressure, that's what we mean. Okay. So one thing we can calculate is the molar volume at STP, right? We can calculate the molar volume of FTP. How would we do that? Well, we know the ideal gas law, PV is equal to nRT, equal to nRT, right? And we know that the volume then, if we solve for the volume, that's nRT over P, right? And for a molar volume, we'd have 1 mole, right? And if we have 1 mole at this temperature and pressure, right, we just substitute in 1 mole times R, 0.08206 liter atmosphere mole Kelvin, right? And then the temperature, the standard temperature, 273 Kelvin, right? And we divide all that by the pressure, which standard pressure is 1 atmosphere, right? And notice again, right? I'm going to be very careful and always cancel my units, right? Kelvin, Kelvin. Notice I end up with liters in the numerator, right? For that, and I get 22.4 liters. Okay. So this is a good number to have in your head at STP. At STP, 1 mole occupies 22.4 liters. All right. Does it matter what gas it is? So the reason that these laws are called the reason it's called the ideal gas law is because it's for an ideal gas, which is pretty much under normal circumstances, any gas. All right. Any gas under normal sort of conditions. We're not going to really talk too much about non-ideal conditions, but any gas. And so that means that it doesn't matter what the gas is. If it's helium and you have a mole at standard temperature and pressure, it's going to have a volume of 22.4 liters. If it's xenon, even though the xenon atoms are much bigger than the helium atoms, 1 mole at standard temperature pressure is going to occupy 22.4 liters, right? Even if you have a molecule like methane, okay? Doesn't matter. 1 mole at standard temperature and pressure, 22.4 liters. It doesn't matter what it is. Why does the size of the molecule or the atom not matter here? Wouldn't you think that going to bigger atoms would cause them to occupy more space? Why doesn't the size matter? Does anybody know?
Because a mole is like 12 dozen, so it doesn't matter how big the eggs are, like it's still 12 dozen, it's a unit of measurement.
right? But here we're asking how much volume a mole occupies, right? And why is it that these smaller atoms occupy the same volume as these bigger ones?
Is there just less of them or something?
No, the same number, 1 mole, right? 6.022 times 10 to the 23rd.
Is it because pressure is directly proportional to volume?
So these all have the same pressure, 1 atmosphere. Remember, what did we learn about the difference between solids, liquids, and gases early on in this course? What was one of the main differences?
How tightly they're held together by the intermolecular forces?
Correct, correct. Remember, solids and liquids are almost touching each other, right? So if you're comparing the volume of 2 solids, and one of them has a larger atom than the other, right? And you have the same number of atoms, the one with the larger atom is going to occupy more volume. Why? Because they're touching each other. But are gas particles touching each other?
No.
No. There's a lot of space between them, right? This is not drawn to scale. If this was drawn to scale, right, this would have to be like 10 feet away. All right? So there's a lot of space between them. Yeah? And because of that, if the atoms are a little bigger, it doesn't matter. They still occupy the same space because the space between them is so much bigger than the size of the particles themselves. Okay? So even if the particles get a little bigger, doesn't matter. They still occupy the same volume. Are you with me? All right, let's see if you can answer this. Given what you know here, which gas sample occupies the greatest volume? Now notice that this is by grams, not by moles. All right, this is listed by grams. So which one of these is going to occupy the greatest volume? Remember, for all gases, 1 mole at STP occupies 22.4 liters. You shouldn't have to do any calculations here. Just think about it. Let me give you another hint. Let's go back to these for a minute. These all occupy the same volume. Do they all have the same mass? In other words, does 1 mole of helium weigh the same as 1 mole of xenon, which weighs the same as 1 mole of methane?
No.
No. These have different masses, right? It takes different masses to get a mole of particles, right? Because they each have a different molar mass. Okay? So now the question is asking, if you have the same mass of several different particles, right, of several different gases, which one has the greatest volume? First of all, would they have the same volume? Yes or no?
No.
No.
Right? Because you can tell here, right? These have the same volume, but they have different masses, right? This is asking you, what if you have the same masses? Which one has the greatest volume? So you got to think about, okay, well, 1 mole occupies 22.4 liters. 2 moles would occupy how much? 44.8 liters, right? So in other words, the more number of moles you have, the more volume gets occupied, yeah? So another way to ask this question is, which sample has the greatest volume? Well, the one that has the greatest number of moles, right? So which one has the greatest number of moles? Don't answer me, answer on the chat. I mean, answer on the poll. Okay, I'm going to give you a couple more minutes. I mean, a couple more seconds. All right, I'm going to stop there. I'm going to share the results. And unfortunately, this is a case where most of you put E, which is the wrong answer, right? They will not occupy the same volume. Why? Because there's different number of particles in these, right? Different number of moles. The one that occupies the greatest volume will be the one that has the greatest number of moles, right? Since the masses are all the same, the one with the greatest number of moles is the one with the what?
See?
Lowest atomic value. Or
The lowest molar mass, right? The lowest molar mass. So the molar mass of hydrogen is lower than all of these. So this will have the most particles. So therefore, it'll have the greatest volume. Okay. All right. Questions? It's hard to think about. If you're a little confused, come back and think about it again a little bit later, right? Remember that what determines, for a given temperature and pressure, what determines the volume is the number of moles, right? If I had 2 moles of this, what would be the volume? 44.8 at STP. Okay, let's do a quick problem. Actually, I'm not going to do a quick problem on molar volume. I'm going to do a quick problem on density. So we also want to look at the density of a gas. So the density of a gas is, just set that down. The density of a gas, like the density of anything, is what? Mass over volume. All right. So we can calculate the density of gases from what we know of the ideal gas law. So let's say we wanted to calculate the density. So let's just set this equation up, this problem up like we normally would. Given temperature is equal to 125 degrees Celsius, and given pressure is equal to 755 millimeters of mercury, right? And given that we have nitrogen gas, right, we're trying to find the density, all right? And what do we know about density? Density is equal to mass over volume, right? Mass over volume. So what we got to do is figure out, okay, is there a sample of nitrogen gas for which we know the mass and we can find the volume, right? Under these conditions, right? So we're given the pressure and the temperature. So notice ideal gas law is pressure, volume, temperature, moles, right? We have pressure and temperature here. We're not given moles, right? So what can we do? We're trying to figure out the mass over volume of some sample of nitrogen. It doesn't matter. So we could just assume 1 mole, right? We can just say, oh, okay, let's assume 1 mole. You can assume any number of moles, but 1 mole is going to be the easiest, right? Just because it's the number 1. So we're going to assume 1 mole. And we're going to say, okay, what's the mass of 1 mole of nitrogen? What's the mass of 1 mole of nitrogen?
28.02 grams, I believe.
Correct, right. It's molar mass, right? The mass of 1 mole. So there's our numerator for 1 mole, right? Now we need the volume of 1 mole, which is the molar volume, right? But notice this is not at STP. Okay, this is a different, so we can't assume 22.4 liters. If this was STP, then we could just assume 22.4 liters and that would be easy, right? But it's not at STP, so what do we have to do?
You need to calculate for the volume.
Right, and of course we're going to use the ideal gas law for that, right? PV equals nRT, so V is going to be equal to nRT over P, right? So V is going to be equal to N. Well, that's easy. 1 mole times R, 0.08206 liter atmosphere mole Kelvin, right? Times temperature. Now the temperature is given as 125, but we need to convert that to what?
Kelvin.
Kelvin. So in Kelvin, that's 398 K. All right, so I'm going to write it in here. Sorry, it's getting a little crowded. 0.98 Kelvin. And then I'm going to divide all of that by the pressure. Is the pressure in the right units? No. So I got to
No.
convert the pressure. So times 1 ATM over 760 millimeters of mercury. That's going to cancel. And my pressure is 0.9934 atmospheres, right? So I'm going to divide all this by 0.9934 atmospheres, right? And that's going to give me my volume, 32.9 liters. Okay. So now notice I have my mass, I have my volume, right? Density is what? Mass over volume, right? So I have to just divide by one by the other. So D is equal to 28.01 grams divided by 32.9 liters. And that's equal to 0.852 grams per liter. Yeah? Okay. Very good. All right. Here's another tricky question. No calculations. Just seeing if you get this concept. Again, it's a little bit tricky, so think about it carefully. Much better. It's looking good. Five more seconds. All right, I'm gonna stop it there. And in this case, yay, most of you got the right answer. So nice work. How do we know that? It's CO2. Well, notice that they all have the same size. So the volume is the same in all of them. The temperature and the pressure is the same. So if volume, temperature, and pressure are the same, what else is the same? According to the ideal gas law.
Same number of moles.
Yeah, same number of moles, right? Same number of moles. So the volume is the same for all of them. The number of moles is the same for all of them, but is the mass the same for all of them? No, right? Because which one is going to have the greatest mass? The one that has the greatest molar mass, right? And the one with the greatest molar mass is going to be carbon dioxide, all right? Because it has a molar mass of 44, right? Argon is 39, and O2 is 32, and nitrogen is 28, right? So it has the greatest mass, and therefore it's going to have the greatest density. Okay? All right, let's move on to talking about molar mass of a gas. So you can figure out the molar mass of a gas. Kind of rhymes, huh? Molar mass of a gas. Say that fast 5 times. Molar mass of a gas. All right, never mind. Calculate the molar mass of a gas at 775 torr and 20. So this is the kind of thing where, again, we're just going to start by writing things down, right? I'm given that the pressure is equal to 775 torr. Remember, a torr is the same as a millimeter of mercury, so we're going to use those interchangeably. Temperature is equal to 27 degrees Celsius. Volume, right? 6.04 liters, and mass equals 9.988 grams, right? So we're given all that information. Where do we have to find the molar mass, right? We're asked to find the molar mass. So the first thing we should ask ourselves is, okay, what's molar mass? What are the units of molar mass? Grams per mole, right? So if we can figure out the number of grams we have, and if we can figure out the number of moles, then we can get the molar mass, right? Notice, what are we given here?
We're given the grams.
We're given the grams, right? Okay, so that's easy. There's the numerator of this, right? How are we going to get the moles?
Gotta calculate.
The ideal gas equation.
Ideal gas equation, right? PV equals nRT. So N is equal to PV over RT. So it's just a matter of getting these things in the right units, right? So P is equal to 775 torr times 1 atmosphere over 760 torr is equal to 1.02 atmospheres. And then temperature is equal to 27 degrees Celsius plus 273 Kelvin is equal to 300 Kelvin, with that being the least significant figure, right? And then we just substitute in the ideal gas law. N is equal to PV over RT, right? We're just going to substitute in, and we're going to get 1.02 atmospheres times the volume, 6.04 liters, right? Divided by the ideal gas constant, 0.08206 liter atmosphere mole Kelvin, right? And then divided by what? T, and temperature is 300 Kelvin, right? So again, we cancel units, liters, liters, Kelvin, Kelvin, atmospheres, atmospheres. We're left with 1 over moles, which is moles. And we get that N is equal to 0.250 moles. Okay, so now we have the moles and we have the grams, right? So we can figure out the molar mass. Molar mass is equal to 9.988 grams divided by 0.250 moles. So that's equal to 39.9 grams per mole. Right? Does that make sense? Alexander?
What are the units for the R constant?
Liter atmosphere over moles Kelvin.
Oh, right. I said it right there. Okay.
Yep.
Cool. Thank you.
Okay. Very good. You guys are doing great today. Thank you. We're covering a lot of material simply because we have an exam coming up, so we got to get through it. But thanks for sticking with me here and doing so well. Our next topic is going to be mixtures of gases. And so one thing about an ideal gas law is when you, ideal gases, when you mix them together, they each behave independently of the others, right? So that means that their properties can be described in much the same way as we can describe the individual gases. We just got to realize that they're mixed together. So the first thing we know for a mixture of gases is that the ideal gas law holds for any individual component, right? But we're going to define something called the partial pressure, which is the pressure in a gas mixture of an individual component of the mixture. All right. So for example, nitrogen, air is composed of nitrogen, oxygen, argon, and carbon dioxide, right? And so the air around us has a total pressure of about 1 atmosphere, right? But it has a partial pressure of nitrogen, which is equal to 0.78 atmospheres, all right? And it has a partial pressure of oxygen that's 21% of the total, so that's equal to 0.21 atmospheres, right? And it has a partial pressure of argon that would be equal to 0.9, oops, that should be 0.009, right? It's 0.009 atmospheres, and so on, okay? So the partial pressure is the, notice that 78, so the total pressure is equal to 1 atmosphere, right? Since nitrogen composes 78% of the gas mixture, right? It also produces 78% of the pressure, right? So its partial pressure is 0.78. Does that make sense? Okay, let me define a couple of equations. The ideal gas law holds for any individual component. So the partial pressure of any gas A is equal to the number of moles of that gas times RT over V. The partial pressure of any other gas B is equal to NB times RT over V, and so on, right? So you have the partial pressure of all the different components you can figure out if you know the moles of that component, all right? And then similarly, the total pressure is equal to the sum of all the partial pressures, right? So if we just sum up all the partial pressures, you get the total pressure, okay? All right, so let's do an example. Here we got to find the partial, okay, so given, we're trying to find the partial pressure of neon, right? In a neon and xenon mixture with a total pressure equal to 3.9 atmospheres, right? And a volume equal to 8.7 liters, a temperature of 598 Kelvin, and xenon is equal to 0.17 moles. All right, so we're given all that. We're trying to find the partial pressure of neon. So again, you know, the art of problem solving, right? How do you look at a problem and figure out, what do I do, right? The first thing you do is what? Sort the information, right? What are you given? What are you trying to find? Then you think, okay, are there any relationships between those two things, right? Are there any relationships between what you're given and what you're trying to find? So right away you see P neon. Sorry, am I back?
Yeah, you're
Yeah,
back.
you are.
Okay. So you have the given and the find, and the first thing you want to do is try to find a relationship between any of those things, right? That's what you're looking for. So notice you have P total and you have the partial pressure of neon. Well, okay, based on this, and by the way, this is called Dalton's law of partial pressure.
Will you lower the page, please? I cannot see on the top.
Yeah, I'm sorry. Dalton's law of partial pressure, okay? So you know that the total pressure, which you're given, is equal to, since there's two components, right? The partial pressure of neon plus the partial pressure of xenon, right? So that's one relationship you know. And again, you're just kind of brainstorming here. Okay, so you know that, right? You know that. This is what you're trying to find. So what else do you need if you want to find this? From this equation. You already have this. You're trying to find out what else do you need?
Xenon's pressure.
Partial pressure of xenon. Perfect. So is there a way you can get the partial pressure of xenon from the given information?
Well, you have the moles of xenon, so.
Yeah. You have the moles of xenon and you have the total pressure and you have, you have the volume, right? And you have the temperature. So I can use this equation, right, to find the partial pressure of xenon, right? So the partial pressure of xenon, right, which I'm going to put into here eventually, is going to be equal to what? The number of moles of xenon times R times T over V, right? And so I'm given all that stuff, so I can just plug right in. Number of moles of xenon is how much?
0.17 mole.
0.17 moles times R, 0.0820, oops. 0.08206 liter. I'm running around the room here. Let me go down here. Number of moles of xenon is equal to 0.17 moles, right? Times R, 0.08206 liter atmosphere mole Kelvin times the temperature, 598 Kelvin, right? That was given, yeah. And then we divide all of that by the volume, 8.7 liters, right? And look what happens. The moles cancel, Kelvins cancel, liters cancel. And what am I left with? What are my units here?
You're left with pressure.
Units of pressure, exactly right. Liters of atmosphere. So if I multiply that all together, I get 0.96 atmospheres. All right, but I'm not done yet, right? Because what am I trying to get to? I'm trying to get the partial pressure of neon. This just gives me the partial pressure of xenon, right? So now I gotta get this equation back and I gotta say, okay, the partial pressure of neon is equal to what? The total pressure minus the pressure of xenon that I just calculated, right? So that's equal to, the total pressure is what? 3.9 atmospheres minus the partial pressure of xenon, which we just calculated, right? 0.96 atmospheres. And then if you subtract that, I get 2.9 atmospheres for my total pressure. Sorry, my partial pressure of neon. Does that make sense? So in the first part here, what I did is I found the partial pressure of xenon, and then I subtracted that from the total pressure to get the partial pressure of neon. All right, good. Let's see. All right. I'm going to let you, there's examples like this on the problem set, so you'll be getting some practice on doing those types of problems very soon. So let's talk a little bit about partial pressures. Again, we're staying on the same topic, but how that works when you are collecting a gas over water. So a lot of times in a chemical reaction that produces gases, of course, if you have a gas that's producing a chemical reaction, it's just going to escape to the atmosphere, right? So if you want to capture it, you got to figure out some way to do that. So one common way is to capture the gas in water. So what you do is you have a beaker like this that you invert and you fill it up with water, okay? And then you have a chemical reaction, let's say like this one. The zinc reacts with hydrochloric acid, it produces a gas. The gas bubbles up, it goes in here, and it then gets caught in this compartment right here, okay? And that's called collecting a gas over water. The problem is when you collect a gas this way, you not only have the gas that you're trying to collect, in this case hydrogen, you also have some water vapor, all right? And the total pressure of the gas in here, right, is going to be equal to the pressure of the hydrogen, which is the gas you're trying to collect, plus the partial pressure of water, all right? And the partial pressure of water will depend on what temperature you're collecting it. And then that's because all water evaporates water molecules, all right? And we'll talk about this a lot more a little bit later in this class, next semester actually. But that evaporation results in some of these water molecules being the gas up here, and that evaporation depends on temperature. The higher the temperature, the more water vapor you have up here, all right? And so you can look these things up. It's very simple. At any given temperature, you have a given pressure of water, all right? It's called the vapor pressure of water. So at 25 degrees, you're going to have 23.78 millimeters of mercury of water, right? And at 30 degrees, you're going to have 31.86 and so on, okay? So, so for example, in this case, right, if this was at 25 degrees, then the partial pressure of water, you just look on this table, you say, hi, it's 23.78 millimeters of mercury, all right? All right, let's do an example using this concept. So you have, I know a lot of examples today. I hope I'm not tiring you out too much. We only have 10 more minutes, so we're almost done. Given that N is equal to 0.12 moles of hydrogen, it's collected over water in a 10-liter container, so the volume is 10.0 liters, and the temperature is 323 Kelvin, all right, which is 50 degrees Celsius, and you want to find the total pressure, right? So what do we know off the bat? The total pressure, right, according to Dalton's law, is equal to what? The partial pressure of hydrogen plus the partial pressure of water, right? How are we going to get the partial pressure of water? We're just going to look on the table, right? At 50 degrees, how much water is going to be there? 92.6 millimeters of mercury, right? So at 50 degrees, the partial pressure of water is equal to 92.6 millimeters of mercury, right? Okay, so we know this. How are we going to get this?
Ideal gas equation.
again, ideal gas equation, right? We solve this over and over again, right? So we know that the partial pressure of hydrogen is equal to the number of moles of hydrogen times RT over V. So we plug into that and we get 0.12 moles times 0.08206 liter atmosphere mole Kelvin. I know it's tedious to write that out every single time, but it's really going to help you. Times temperature, 323 Kelvin, right? Divided by the volume, 10.0 liters. Cancel units, right? Liters, liters, moles, moles, Kelvin, Kelvin. I'm left with atmospheres. Yay. So the partial pressure of hydrogen is equal to 0.318 atmospheres. All right. Now, if we want we got to get this to the same units, right? Because this is in 92, this is in millimeters of mercury. This is an atmosphere. So we can just convert that to millimeters of mercury. 0.318 atmospheres times 760 millimeters of mercury per 1 atmosphere. Atmospheres cancel, right? And I get 241.8 millimeters of mercury, right? So my total pressure is going to be equal to the pressure of hydrogen, which we just calculated, 241.8 millimeters of mercury, right? Plus what?
92.6.
Correct. 92.6 millimeters of mercury. So the total pressure is 330 millimeters of mercury, or 3.3 times 10 to the 2 millimeters of mercury. I'm writing it out this way just to get the right number of sig figs in there. Whew. Does that make sense? Lot of example problems here of applications of the ideal gas law. Okay. So you'll just be playing around with these and get a lot of practice with them as you work through your problem set. Any questions?
Yeah, I got a question.
Yeah.
You can only assume that it's 1 mole when it's at the standard temperature and pressure, right?
What you can assume about 1 mole is that if you have a mole of gas at STP, it's going to occupy 22.4 liters. So those things all go together. 1
Okay.
mole, STP, 22.4 liters.
Okay. Got
Okay.
it.
Taylor, do you have a question?
Yeah. So this vapor pressure of water, is it based on some kind of constant, or is it just a bunch of measurements that we've collected?
There is an equation that governs it, which would be something that we would cover next semester.
Okay. Okay. So
Yeah.
just look at the chart for now.
Yeah, for now, we're just gonna look at the chart. The vapor pressure, basically what happens is as the temperature goes up, the water molecules are moving faster and faster, and most of them more can break free and become a vapor, right? At 100 degrees Celsius, the vapor pressure is 1 atmosphere because it's boiled.
It's overcome the atmosphere.
It's overcome the molecular force. Yeah, exactly right. Yeah.
Okay.
We'll
Okay.
talk more
All right.
about this next semester.
All right. Thank you. Sorry, I was just curious.
All right. Real quickly, my last 5 minutes here, I want to revisit stoichiometry, right? So remember, we looked at stoichiometry when we looked at chemical reactions, and remember the pattern? What was it? Mass to moles
Moles to mass.
to mass, right? Remember that, right? We did a lot of calculations like that for stoichiometry, all right? And then we revisited stoichiometry in solutions, right? And we found that we can go from volume and molarity to what? To moles, to volume or molarity or whatever we're asked to find, right? Now we're in gases, right? And so if we have a chemical reaction that involves gases, let's say A goes to 2B, right? We can go from P, V, and T of gas A, right? To what? Moles of gas A, to moles of gas B, to whatever it asked us, right? Back to PV and T, or to mass, or whatever it wants, right? And again, the very important thing is this part of it, right? This conversion here comes from the balance equation, right? In this case, it would be 2 moles of B for every 1 mole of A, right? That's your stoichiometric relationship that comes from the balance equation, right? And of course, this, to get from here to here, we just use what?
The ideal gas equation.
The ideal gas equation. Okay, so real quick here, we're given 0.12, no, sorry, that's not the one I want to do. I just did that one. We'll do this one. Actually, this one, instead of writing it out, I'm just going to do it on the PowerPoint here. How many grams of water, all right, so we're trying to find mass of water, form when 1.24 liters, so we're given the volume of the gas, we're given the pressure of the gas, and we're given the temperature of the gas, right? So we're given P, V, and T of some gas, right? And we're trying to find the mass that forms of this, right? So notice the conceptual plan. We're going to go from liters, right? And actually not just liters, but pressure, volume, and temperature, right? Which are all given, to moles of hydrogen. And then we're going to go to moles of water, and it's 2 to 2 here. And then we go to grams of water, right? Do you notice the pattern? It's very, very similar to the stoichiometric relationships we've been doing all along, right? The only difference is that you start off using the ideal gas law to get to moles instead of going from grams to moles, right? So there you go. We'll start with 12.4 liters, right? The liters cancel, we go to moles. Because it's at STP, we can use, we don't have to solve the ideal gas law equation. We can just say, okay, I know at STP, 22.4 liters is 1 mole. And it doesn't matter what the gas is, right? And then here's our stoichiometry, 2 to 2, right? And then going back to grams of water, and there you go. Okay. All right. I think we're out of time, and I've probably exhausted you. Thank you for paying attention. I know those were a lot of problems. We will just talk about these last couple of things on Monday. And we will have a short review for the exam. My son, who is in Boston, needs to have surgery on Friday. So I'm actually going to fly out to Boston tomorrow and be with him and take care of him over the weekend. So Monday, I'm going to be in a hotel room in Boston when I talk to you. And so I hope everything will go well. I'm bringing my computer, obviously, and everything else, but I just wanted to warn you ahead of time that I'll be communicating to you from there, and the background's going to be a little different, and maybe the sound, I don't know. I'm a little bit nervous about it, but I think it's all going to work out. If for some reason something happens and it doesn't work out, look for an email from me, okay, with a lot of exclamation points in it. He broke his fibula, so he has to have surgery on his leg, but he's out there just on his own, so he doesn't have anybody to really watch him, and so I'm gonna fly out. He's about your age, by the way. So okay, thank you guys. I hope you have a great day. Remember, this problem set is pretty long, right? Hopefully you've already started on it. There's lots and lots of opportunities for help. Make sure you go to the Canvas webpage and see all the times that the tutors are available. Again, one way you can work is if you can be working on your problem set while you're logged into the Zoom session for the tutor. And then as you have questions, you can just ask them, right? The tutors are really, really good and they're there to help you, okay? Tomorrow, during my normal office hours, I will not be available because I'll be flying to Boston. I will be available if you need me sometime over the weekend. You can call me, you can text me, sorry, you can email me, and we can set up a Zoom call from over there. But take advantage of the tutors, and the next few days, today, tomorrow, and Friday are going to be important days for you to make sure you're understanding the material that you're on now, and also to begin reviewing for the exam. All right, you can start doing the pre-test tomorrow, right? We've covered almost everything you need to know for the exam, except for a last couple of things here in chapter 5, all right? But pretty much everything else we've covered for the exam in lecture. You should be ready to go. You can do most of the pre-test. You can finish your problem set that's due Friday, and you can even start on your problem set that's due Wednesday, all right? I'll be sending out an email about next week like I normally do. But because of the exam on Wednesday, there's actually a shorter problem set that's due Wednesday as well, instead of the normal Friday problem set, so that you do it before the exam. Okay. But again, I'll send out an email with all those details, and I'm going to end class because I've gone over. Thank you very much for your attention. I hope you all have a wonderful, wonderful evening, and I'll be here. I'm going to stay on for those of you that have questions. Otherwise, thanks again for having your cameras on. I love seeing your faces and nodding yes, and seeing you work things out on your calculator. And I know that you're engaged. So thank you for having your cameras on, those of you that do. And I'll see you all on Monday, fingers crossed, from a hotel room in Boston. Bye.
Thank you.
Thank you.
Thank you.
Hey, Professor, would you mind putting the last problem back on the screen?
Not at all. This one?
The one that you did on the PowerPoint.
Oh, yeah. This one.
Thank you.
Yeah, no problem. Abe, did you have a question?
Yeah, yesterday I got a problem on the problem set with rubidium, and I just wanted to know if that was another exception for when a substance is when a compound is soluble.
No, there are no exceptions with rubidium, right? Let's just pull up the solubility rules here real quick. Oops. Oh, that's the wrong thing. Hang on for a minute.
It was with rubidium and sulfur, and I was just curious because when I said that it was insoluble because sulfur is genuinely insoluble, I got the question wrong. But when I indicated that it was soluble and no reaction occurred, the answer was correct.
Let's see here. Sorry, so what was the compound again?
Give me a second. Let me just, I wrote it down. It was
Sulfide with rubidium?
I'll give you the exact problem right now. It was
rubidium bromide and calcium sulfide.
That's what it was. Yeah, rubidium bromide and calcium sulfide.
So calcium and sulfide, right, will form a precipitate. So wait, so the reaction was, let's see, let me move this over. Tell me the reaction again.
It's rubidium bromide and calcium sulfide, and the possible products would be rubidium sulfide and calcium bromide.
Right. So So you got rubidium sulfide and calcium bromide. So calcium bromide is soluble and rubidium sulfide is insoluble, right?
That's what I thought at first, but I got it wrong. As
No, wait, no, sorry. So it's sulfide here, right?
Huh.
Sulfides are generally insoluble.
Yeah.
And, oh, I see the problem. It's just not on this. I see the problem. Yeah, it's just rubidium is a group 1 metal.
Uh-huh.
And so it belongs to this group of metals here.
Okay. Yeah, because I saw another table online where I think might have fluorine. I think fluorine was another exception. Or it was fluorine or francium. Give me a sec. It was
So rubidium, yeah, it's a group 1 metal. So it behaves kind of like potassium. I just don't have it in this table. Sorry about that. Okay, so what problem was that? That wasn't a very fair problem. I think I'll just give everybody credit for that because that's not on the table.
I can give me a sec.
I can look it up too. I can find it.
All right. Yeah, I don't know which one it was. It's within the first 10. That's all I remember.
Okay. I'm gonna give everybody full credit for that one because that was my mistake. Thanks for asking. Oh,
Yeah.
Still being recorded. Yes, thank you for that as well.
And then